Of this morning. Our first speaker in this session is Leszek Kolodziejczyk from the University of Warsaw and currently at the University of California in San Diego. And he's speaking about Toda's theorem in bounded arithmetic with parity quantifiers and bounded depth proof systems with parity gates.
Thanks, Jan. Let me also thank the organizers for making it possible for me to come here. I'm going to talk about work that's joint with Sam Buss and with Konrad Zdanowski. And the work is related to one of the major current open problems in propositional proof complexity. The problem of proving strong lower bounds and ideally exponential or almost exponential lower bounds for bounded depth proof systems with parity gates, with counting mod 2 gates. So these are more or less your textbook proof systems, except that you put a limit on the depth of a formula that may appear. So that would give you your regular constant depth proof systems. On the other hand, you do have an additional syntactic construct, namely a parity connective, which takes some number of inputs and outputs a 1 exactly if the number of those inputs which are evaluated to 1 is odd. So these systems are called bounded depth Frege systems with parity gates, also called ACC0 mod 2 Frege. And unlike the case for constant depth systems without the parity connectives, we don't have lower bounds for them. And there is a related problem about a theory in bounded arithmetic that's closely connected to these systems. The theory is basically bounded arithmetic with a parity quantifier and an additional uninterpreted predicate alpha. And the problem there is to prove an interesting independence result. I won't try to define what interesting means, but basically proving independence of some version of the pigeonhole principle from that would be interesting, as opposed to something that you could get from Gödel's incompleteness theorem or something of that sort.
What is this? Remind me. The ACC0 as opposed to AC0. What's the second C0?
So I think the second C is for counting. So that's having mod 2 gates.
Oh, the mod 2 gate. Okay. This is wasteful notation. Characters.
It's not my notation. Okay, so the problem of getting lower bounds for these proof systems has long been described and thought of as a hard problem that's probably doable, in particular because we do have lower bounds for the corresponding circuit class, but now it's been described as doable for a number of years and hasn't been done. So maybe there are some issues, and it does seem that we don't have a good enough understanding of the power of these proof systems. So our work is a contribution towards that understanding. So we're not going to try to get lower bounds right now. We're trying to gain a better understanding of these constant depth systems with parity gates. There is a natural analog of these systems with mod p gates as opposed to mod 2 gates for some other prime p. You could basically say, give a similar talk to mine about mod 3 or mod 5 or whatever. For simplicity, I'm going to concentrate on mod 2. So here is a result. Here is an important result about the power of counting mod 2. Toda's theorem in a slightly non-standard formulation, I guess. The polynomial time hierarchy with an additional parity quantifier, in addition to the usual existential and universal quantifiers, collapses to BP parity P. So parity P is the class that counts numbers of positive instances to a polynomial time problem mod 2. The paradigmatic problem is parity sat, the set of formulas that have an odd number of satisfying assignments. And BP parity P is the class of problems that you can reduce in probabilistic polynomial time to parity P. So Toda's theorem says that the polynomial the parity version of the polynomial time hierarchy collapses to BP parity P. And if you look at its relativized version and think of it in terms of the correspondence, the natural correspondence between the relativized polynomial time hierarchy and constant depth circus, then after a little bit of a small bit of work, you see that this is actually a result that can be interpreted as a collapse result of bounded depth circuits with parity gates to some very simple form corresponding to this BP parity P class. The increase in size is quasi-polynomial, as usual, this polynomial hierarchy constant depth circuits correspondence.
What is exactly pH parity?
What is exactly pH parity? So this is probably most neatly defined in terms of quantifiers. So you close polynomial time under the typical polynomially bounded existential, universal, and parity quantifiers. Yep.
So isn't it the same as the mod P hierarchy, the mod 2P hierarchy? So you just take mod 2P, raise it to the power mod 2P and so on, the alternating hierarchy.
Is it the same? Actually? Okay.
I think so, I don't know.
I'm not sure. So, but that has to be a somewhat non-trivial result, right? If you just apply the mod 2 thing. That must somehow follow from this, right? It's
Well, no, but the proof, it simulates NP and BPP to the parity P, so. Yeah, but anyway.
okay. Okay. Well, possibly. I mean, so the question is, we have this collapse result for circuits. It's natural to ask whether we can do something similar for proofs. And as a matter of fact, already a pretty long time ago, in the mid-90s, there was a sort of collapse result for bounded at Frege with parity gates. This was done by Messiel and Pitassi, mid-90s, I think it was published in 98. The thing though there is that they prove that constant depth proofs with parity gates can be simulated by proofs of a particularly simple form, but it's not an actual collapse result in the sense that the proofs of simple form they get use exact counting gates. They use threshold gates to be exact. So it is not really a collapse result for bounded Frege with parity, and in particular, the new system uses a connective that's more powerful than the original connective. So you're not sure that you have gained anything by this reduction.
May I ask you about this Toda theorem? I don't remember it well. So you say it's a collapse, so this means that pH plus is equal to BP times.
BP parity P, yes,
No,
yes.
That's a subset. It's equal.
Yes, I mean BP parity P is a subset of this hierarchy by the usual BPP in polynomial time hierarchy argument.
Okay.
So this is an actual collapse result, yes. So one thing that's changed since the Messiel-Pitassi results is that in bounded arithmetic, which as I mentioned is very closely tied to these constant depth proof systems, it has turned out, thanks to Emil Jerzabek's work over a number of years, that you can actually do approximate counting reasonably well, and that you have well-behaved notions of probabilistic complexity classes, in particular various BP whatever classes. So this suggests that it might be possible to prove Toda's theorem in bounded arithmetic with a parity quantifier. That should give you some sort of collapse result, and you could see what that means for constant depth Frege proofs with parity gates. And that's exactly what we've tried to do. So let me say what I'm going to try to do in this talk. I'm going to define a bunch of bounded arithmetic theories, prove a collapse, or tell you that a collapse can be proved of bounded arithmetic with a parity quantifier to one of these theories, define proof systems corresponding to those theories, and get the corresponding collapse result on the propositional level. The proofs that are behind this talk are, in my opinion, somewhat unappealing. It's largely a matter of coming up with the right definitions and then doing some technical work. There's no really nice combinatorial proof idea or anything hidden behind this. To reflect this, I'll try to make the talk comparably unappealing. So, well, you have been warned. Anyway, let me quickly go over what bounded arithmetic is as a quick reminder. So basically you have some first order language of arithmetic so that bounded formulas in this language with I bounded quantifier blocks correspond to the ith level of the polynomial time hierarchy in the sense that they define exactly properties from that level. The class of, or the existential class with I bounded quantifier blocks is called sigma bi. Then you define a hierarchy of theories Ti2, never mind what the 2 stands for, and Ti2 has induction for properties in the ith level of the polynomial time hierarchy. T2 is the union of the Ti's overall natural numbers I. There is also, there are some subtleties concerning T02. Let me just say that in some sense the right notion of T02 is a theory called PV, which has induction for all polynomial time properties. This all can be relativized, just like complexity classes can be relativized, and this is done by adding a new uninterpreted predicate alpha, and which represents an oracle, and you're then able to use this in induction formulas. Bounded arithmetic is closely tied to computational complexity by means of so-called witnessing results. What interests us more in this particular talk is the connection to constant depth propositional proof systems. This is because of a sort of translation commonly called the Paris-Wilkie translation. Basically, if you take a bounded arithmetic formula with this uninterpreted oracle predicate in it, you replace all atoms using this predicate by variables, all atoms without this predicate by true or false according to their truth values, and then you replace bounded quantifiers by corresponding connectives. You get a family of fixed depth propositional formulas. Moreover, this also works on the level of proofs. Proofs in each of these Ti2 alpha theories translate to constant depth proofs of a fixed depth. Of a depth that depends on I. And I never remember whether it's I minus 1 or I minus 1.5 or whatever, and that actually depends on how exactly you define depth. So I won't get into that now. I mentioned that bounded arithmetic can do approximate counting. So the thing you need for that is this extremely natural principle here called the surjective weak pigeonhole principle, which says, it's kind of dual to the usual pigeonhole principle. It says that you can't map a smaller set surjectively onto a larger set, and since it's a weak pigeonhole principle, then the set should be much larger. The typical version would say that you can't map a set of size A, make it the interval from 0 to A, onto a set of size A squared, for instance. A slightly stronger version is needed for the actual approximate counting, but in many contexts you can ignore this issue anyway, so just think of the principle saying that you can't map A objects onto A squared objects surjectively. And well, this is of course stated about a certain specific class of functions gamma. The two versions that matter for us here is this surjective weak PHP for polynomial time functions and for polynomial time with an NP oracle. So the bounded arithmetic theories that the important thing about this principle is that it is provable in bounded arithmetic. So that's something that's essential here. So the theories that are used for Emil's approximate counting are these two guys here. I call them APC1 for approximate counting 1 and APC2. So APC1 is just the basic theory for polynomial time, but you have to add the surjective weak pigeonhole principle for polynomial time functions. And in that theory, which lives on the second level of the bounded arithmetic hierarchy, it lives in T22, you can talk about the approximate size of a polynomial time set up to a 1 over polylog fraction of the interval it lives in. So this is a very useful thing, but its major weakness is that you can't really count sparse sets well. So if the natural ambient interval of a given set is much larger than the set itself, that set won't really be distinguishable from the empty set by this sort of counting. So the stronger theory, which is basically APC1 relativized to NP, you raise everything by one level in the polynomial time parity, can do the old type of approximate counting for P to the NP sets, but for NP sets, in particular for polynomial time sets, it can do better. Namely, it can basically measure the size of a set up to a 1 over polylog fraction of that size itself. And this is expressed in some way in terms of surjections. Okay, so for every NP set, there will be an M such that we have witnesses for the fact that the size of the set is at least M, but not larger than M plus M over some polylog fraction of M.
So is it the case that this exponent for the log doesn't matter, that polylog, it's going to be the same?
Well, you can get surjections for every exponent, basically. Okay, so whatever exponent you take.
No, the question is, so if you add, say with the surjection a plus a over log a to the c, does the theory depend on?
There's a theory.
No, when you're adding the weak pigeonhole principle over fp to that, does it depend what the exponent of the polylog is? I'm not sure.
So you're adding the
I think the question is about line 2.
line 2.
Whether it would make any difference if you put an exponent c on it.
No, that's going to be an equivalent theory, which is some kind of yeah. After a while of thought, it's actually maybe not immediate, but there is some kind of easy trick to show you that it's an equivalent theory. Okay. So that was about approximate counting. Now, regarding counting parities. So there are two natural ways of allowing the parity quantifier to appear in boundary arithmetic theories. More precisely, there is one more natural way and one less natural way that we found useful in the context of our work. So the natural work is just to have a new syntactic construct. There is an odd number of x smaller than y quantifier, and you allow it everywhere. You can nest it arbitrarily. You can put it in front of any bounded formula, and so on. And the theory you get when you allow induction for such a class of formulas is called T2 parity. A version that we found useful is to allow the parity quantifier to appear only in front of formulas that syntactically correspond to polynomial time properties. So you're only allowed to count parities of polynomial time formulas. And then if you take the class of bounded arithmetic formulas with I blocks of the usual bounded quantifiers and atoms replaced by these parity P constructions, you get a theory, you get a class of formulas that you could call sigma bi parity P, and the corresponding theory would be Ti parity P. So
that's the definition of Ti.
Yes, that's a definition, I mean, or a trace of a definition. But I hope it's detailed enough to give you an idea of what the formal definition is. So our result is basically the following. You can define the notion of BP parity P correctly in the second theory for approximate counting, APC2, relativized to the parity P properties. And moreover, and more importantly, you can then prove that there is a correct translation of all bounded formulas with the parity quantifiers into formulas representing BP parity P properties. And this translation is correct in that particular theory for approximate counting with relativized to parity P. What provably correct means is that you can show that this this translation commutes with connectives and quantifiers. In the case of the parity quantifier, which isn't even allowed in some cases as a syntactic construct in this weaker theory, it's only allowed in some very specific places, correctness with respect to that means satisfying the natural axioms for a parity quantifier. So if a set is odd up to n, and it's satisfied at n plus 1, then it's even up to n plus 1, and so on. And there are no problems with relativizing this. So basically, APC2 parity P proves Toda's theorem. And there are no problems with relativizing this to an oracle. I'm not going to say much about the proof. It is essentially a formalization of the usual proofs that you could find in a textbook. There are, of course, some technicalities involved because, well, for instance, the approximate counting mechanism that's available in boundary arithmetic requires some care when using it, but basically it all works. I just wanted to point out one specific place where this better counting theory, the second counting theory, seems to be needed. So the proof in general is by induction and on formula complexity. You just inductively translate the stuff. The base case is essentially the Valiant-Vazirani theorem. So that's a probabilistic reduction of SAT to unique SAT. For a satisfiable formula, you typically, with high probability, you transform it into a formula for one satisfying assignment. For an unsatisfiable formula, you get an unsatisfiable formula. So in the proof of the correctness of that translation, at one point you need to know that given some propositional formula, you can approximate the size of the set of satisfying assignments up to, say, a factor of 2. So you'll have surjections witnessing that the set has size at least 2 to the k and at most 2 to the k plus 1 for some k. So this is exactly the sort of thing that does not work in the weaker theory for approximate counting. You can try to come up with a more unorthodox proof of Valiant-Vazirani or Toda directly, somehow avoiding this exact line, but no matter how you try to push the pieces around, you're still always left with some place that apparently needs the stronger type of approximate counting. So it is open whether this can be done in APC1. Right, so let me move on to the proof systems quickly. So to these somewhat hybrid theories with Boolean usual quantifiers at the top and parities at the bottom correspond some somewhat ugly and hybrid propositional proof systems. The system we call PCKI has lines that are sedents, meaning, well, sets of formulas separated by commas. The comma is interpreted as a disjunction. And then the formulas have all alternations of and or, unbounded Fanon and an or. And at the bottom, instead of literals, you have polynomials over the two-element field. And, well, the idea, which is somehow enforced by the definition of proof size in this system, is that these polynomials are low degree in some sense. Typically, they're logarithmic degree in the size of the proof. The intended meaning of a line consisting of a single polynomial is that it's 0. Conjunction and disjunction work as usual. The comma is interpreted as disjunction, so that's a more or less Tate-style calculus in logical terms. It might not be immediately clear that this is actually a subsystem of the constant depth Frege with parity P systems, but it is basically because a low-degree polynomial is essentially a parity connective applied to monomials meaning small conjunctions. Low-degree monomials meaning small conjunctions, and you could actually work directly with that, though I find the polynomial formulation somewhat more natural, and I find it smoother to work with. Sam actually disagrees, so it's a matter of taste. The rules are more or less what you'd expect. So on the connective levels, you have the usual rules for and or, and so on. You have weakening and cut. On the level of polynomials, you have algebraic rules. If a polynomial is 0, then multiplied by anything, it remains 0. If two guys are 0, then their sum is 0 as well. So these systems correspond to our theories in the sense of a typical Paris-Wilkie style translation. Essentially, the thing is that if you prove a formula of the appropriate complexity in the ith theory in our hierarchy, then its negation is going to be refutable either in PCK I-2 or by a tree-like proof in PCK I-1, and both are going to have quasi-polynomial size, so both will have won't be enormous. It's interesting to note what happens for the case where where the index would be -1. So basically, if you consider the propositional translations of sigma B1 parity P consequences of T12, then that translates into quasi-polynomial size polylog degree proofs in the polynomial calculus. So just polynomials as lines, just algebraic rules, as in Massimo's talk a while ago. If you consider consequences of the same level, but of the base theory, of the theory for polynomial time with a parity P oracle, that corresponds to polylog degree proofs in so-called Nullstellens, that's what I think appeared in Sam's talk yesterday. Basically, you can think of it as tree-like polynomial calculus proofs. So, this translation in connection with the collapse on the arithmetic level by standard general nonsense about reflection principles and so on translates into a collapse on the propositional level. Namely, if you just consider, oh, I forgot to mention this explicitly, but what was on the slide. So a consequence of this correct translation of all bounded formulas into BP parity P properties is that the second theory for approximate counting relativized to parity P has the full strength of bounded arithmetic with parity quantifiers. The stronger theory is conservative over the weaker theory. So in particular, since the second approximate counting theory lives in T32, the big theory is conservative over T32. So that translates into the following collapse on, or simulation result on the propositional level. If you have a simple enough formula, simple enough to be expressed as a line in some sense in the weaker proof system, then constant depth Frege with parity gates is simulated with a quasi-polynomial blow-up in size by the system corresponding to T32, namely this PCK1 system. So sedence of ands of low-degree polynomials. If you, I'll skip the proof because I'm running out of time. If you actually use the other result, namely the conservativity over the counting theory, instead of just over T32, then what you get is a collapse result on the propositional level to the tree-like version of the system with just sedence of polynomials as axioms, as lines, but with additional axioms corresponding to the weak pigeonhole principle. You could even, if you really wanted to, invoke some results in logic to get a collapse to polynomial calculus with some axioms corresponding to a variant of the weak pigeonhole principle, but those I find slightly less natural, so maybe that's debatable which formulation is better. So bottom line, the picture that emerges from this work on the bounded arithmetic level, although I've tried to indicate the corresponding proof systems as well, those are in blue, is that bounded arithmetic with a parity quantifier, well, the whole potential hierarchy of sub-theories of that collapses to these four guys here. So the natural question is, we would like to have a lower bound up here, so the natural question is where we can actually get lower bounds or corresponding independence results. Let me end with that. So the ones that we do have, and this mostly follows from known work by either immediately or with some kind of not too much additional effort, is that this theory here, which corresponds to polynomial calculus, to low-degree polynomial calculus, we can have an independence result for that because we have lower bounds for degree in the polynomial calculus, for instance, for the pigeonhole principle. As for these theories with some amount of the approximate accompanying mechanism, the surjective weak pigeonhole principle, you can do some stuff if you allow the surjective weak pigeonhole principle only for functions that don't involve parity. So if you took this theory and restricted the pigeonhole principle it contains to functions that don't involve parity, then by switching lemma techniques with Null-Stellensatz lower bounds, you'll get a lower bound for that. It's very difficult to do anything, in my opinion, for theories, even just this first theory, if you allow parity in the surjective weak pigeonhole principle. And I'll end by putting up my last slide, which kind of explains what, in my opinion, the difficulty is, because I think the difficulties are essential. This is quite potentially the main source of difficulties with dealing with the constant depth systems with parity gates. So thank you very much. Let me finish here.
Maybe one or two quick questions. Jan, I guess.
So what is the difficulty?
So, well, basically, when you start thinking about these axioms corresponding to the surjective pigeonhole principle for parities, well, you start thinking how you could take advantage of them. I mean, how to get a handle on them. So the only thing you can naturally come up with, the only feature that they have, they're not syntactically special in any significant way, is their probabilistic properties, that they're somehow always true or something. And basically, the problem is that, so you would like briefly put to show that there are formulas that can't be true, that can be proved even in, say, Null-Stellensatz with additional axioms that are almost always true. And simply put, that's not true. So a randomized version of Null-Stellensatz, where you are allowed to use additional axioms that are almost always but not always true, proves all tautologies.
Well, there was this, extended Null-Stellensatz, the one with extended extension axioms which exactly corresponded to constant depth Frege system with parity. And it had this property that, well, just this property you mentioned.
Right, but there I guess you did not observe the collapse in depth in any
No,
way, right? Yeah.
I'm just saying that this.
Yeah, that's true.
I have a quick question. Could you put back, if possible, the last third or fourth slide where you describe this simple enough formula, where you have this alternation of or, and, or, parity? Yeah, this one. So what do you mean by that top line, or, and, or, parity? Is that
So the simple
a
enough,
particular form or formula?
yeah. So the simple enough here means that the formulas should be ors of ands of ors of parities of small things.
Parities are at the bottom.
Yes, parities are at the
Oh,
bottom.
no, they're small conjunctions.
Yeah, of small conjunctions specifically. And
Conjunctions, right?
yeah, so it's ors of ands of ors of parities of small conjunctions. Yes. And the reason for that is simply you have to be able to express that in the proof system, or its negation rather. So
In the fourth or fifth line, that what do you mean? Ors of ands of
yes, ors of ands of parities. So those are the formulas that you can simply have as lines or as sets of lines in the corresponding proof systems. The stronger ones, if you wanted to think about formulas of a greater but still fixed complexity, you could redefine these systems to allow all formulas as lines, but cuts only for the formulas that I used to describe that. And the collapse result would still work as long as you do it for families of tautologies of fixed complexity, though the complexity could be higher than the I in PCKI.
So since it's getting rather late, I suggest that any further questions we ask directly to Leszek in the break. And we thank Leszek again for